Okay. All right. Sorry about that delay. I'd say I feel very lucky to have kind of a nice talk just preceding mine by Joe, which kind of covers a lot of similar ground, or kind of gives a nice introduction to the compost bomb problem. So this work that we've been doing is based on foundations. So on the paper, the original paper by Luke and Cox, which kind of introduces this simple kind of box model, compost bomb model, and some papers by Sebastian and Claire Perryman and Peter Ashland that kind of go into the geometry which underlies this kind of rate-induced tipping point, which we see within the compost bomb model. So I won't go into too much detail of the actual box model, because I think that Joe kind of covered the different processes that go on here, only to say that we are looking at a simple 2-parameter model. So we've got soil temperature and soil carbon, and we have 3 processes which are the equilibration of soil temperature to atmospheric temperature, dependent on the alpha, productivity, which is this parameter pi, which puts carbon into the soil through litter fall and stuff. And then this respiration term, this microbial respiration term, which is kind of the starting point for our paper. And again, the question just at the end of the last talk kind of preempts where the direction that we've gone with things. So the original microbial respiration term of Luke and Cox is an exponential function which grows kind of without a bound in temperature. So we replaced it with a kind of a Setch-like function, which has kind of an exponential growth followed by an exponential decay, with a kind of a maximum at a point of your choosing, right? So you can pick it using this TS max parameter. And if you send TS max to infinity, you recover the old respiration function in the limit, right? So we kind of get a more realistic representation of microbial respiration. And additionally, the model becomes more numerically stable because the exponential makes things change quite fast, and solvers can have some problems with it. So looking then at the 2-dimensional phase space, we kind of get this nice geometry. This is kind of comparable to the geometry which Sebastian and his collaborators had in their papers. The difference being that we now, in the critical manifold here, have this kind of branch which before was flattened, which allows trajectories to kind of shoot off to infinity, but now kind of sticks upright and catches trajectories before they get to large soil temperatures. And we can kind of see this better if we overlay it with a couple of trajectories from the full system. So this critical manifold, this kind of gray bar, comes out as a result of the slow fast analysis and geometric singular perturbation theory, which gives you the underlying geometry of the system. So now we have our nice model with our nice microbial respiration, which dies off. The natural next stage is to try and look at it under different climate forcings. So we've taken this in 2 separate directions. So the first is to look at it under kind of a slow climate change. This was also looked at in the original Luke and Cox paper, which is just kind of a global warming. But they looked at a constant temperature ramp, whereas we taken in a different direction, and we look at a tangent function which rises from some lower temperature TA minus to some higher temperature TA plus. The second scenario then is this kind of a fast climate change scenario, a hot summer impulse. So we have this Setch function, which, like our microbial respiration function, is kind of like a little bump from TA minus to TA plus, to try and recreate or understand what would happen to the model under extreme weather scenarios. And I think some motivation for a need to look at that was given by Joe in his last talk. But the upshot is that these 2 forcings, the first one is slow and the second one is fast, end up with 2 quite different geometries to actually explain the rate-induced tipping points and transitions that we see in the model. So the first step, I suppose, with these model forcings is a process called compactification. So our model forcings give us a non-autonomous system because they're time dependent, which is a problem because you have no equilibria or anything to kind of latch onto in phase space. But because we've chosen four things that die off as time goes to negative infinity and positive infinity, we can kind of attach the dynamics at positive and negative infinity to the phase space in a process called time compactification, which is kind of a reference here for which goes through the details. But the upshot is that we are able to have as part of the phase space the dynamics in positive infinity and in backward infinity, which give us equilibria and things to hang on to, and they make our system autonomous. So this allows us then to do our geometric singular perturbation theory and the slow fast analysis before to get a picture of the geometry underlying phase space. So here, S is the compactification variable. So time goes from -1 to 1, right? And kind of this infinity is kind of compactified into this space. And you can see we gain this equilibria E minus and E plus in the backward and forward time limit that allow us to simplify this rate-induced tipping problem to a problem from, or the question which we now have to ask is, if you begin near this E minus, when do you leave this stable sheet in the critical manifold and pass this other stable sheet of the critical manifold? So we are able to formulate the question in terms of equilibria. Further still then, from the slow fast analysis, we can reduce this problem again through desingularization to find critical points along this fold, which become equilibric through desingularization. And the upshot is eventually we can simplify this whole rate-induced tipping problem to connections between equilibria. So when does E minus connect to equilibria which sit along this fold F1? And that's nice because heteroclinic connections are something that are kind of easy to do, something we're familiar with, know how to do, and something we can actually calculate, and allows us to come up with come up with a diagram like this, where on the x-axis here we have the magnitude of our climate change shift, and on the y-axis we have the actual rate of the shift. And in gray here we have everything which tips, and in white we have everything which tracks. So the boundary is given by this red line here, which is a heteroclinic connection from E minus to these folded equilibria which sit on the fold. And we end up with two kind of cases within that because we connect to different types of equilibria. There's a simple case here on the left and a complicated case here on the right. So we could have a look at what the actual phase portraits look like in the reduced system, which show us how the tipping actually occurs. This is the more complicated case. So if we fix the magnitude of the shift and we increase the rate, we begin with kind of no tipping region at all, and then this gray tipping region which grows as we increase the rate and eventually swallows up E minus, at which point we will say that that's our rate-induced tipping. So you can compare this calculated rate-induced tipping point, which occurs in this epsilon equals 0 limit, with the numerically calculated region from the full system. And the agreement is quite good because this epsilon is actually not as small as you might like for the slow fast analysis. And the fact that it's a complicated case is somehow reflected in these kind of accumulating tipping tongues that we get from below. In the case of fast climate change then, which is our novel case, the geometry is very different. There's no critical manifold. Instead, what we have is the dynamics, the majority of the dynamics taking place in this fast layer plane, which again gives us these additional equilibria and allows us to formulate the problem of rate-induced tipping in terms of connections, heteroclinic connections between equilibria. When we do that, then we again get this red curve, which matches up quite closely with the numerically calculated one for epsilon is greater than 0. There is a slight additional complication with this case because the nature of the stretch, the bump function, is such that as you increase the rate, your bump kind of becomes narrower and narrower. You get shorter and shorter hot summers, and eventually you become too short and you stop tipping. So there's another distinction between this kind of fast climate change and the slow climate change, which is reflecting the fact that the tipping region actually cuts off at the top, and we get this nice tongue. And this is kind of just a picture of the phase portrait of the actual transition. So just to summarize, we kind of modify this respiration function and look at it under two novel climate forcings, or one very novel climate forcing, and give a nice framework for how to analyze each forcing.